Hey everybody, starting in a couple minutes here.
Oh, James,
Yeah,
I think for oh wait, where's my speakers?
you're on. Oh.
Okay, there we go. I think for some people they might come in late because today there some people who are living in the dorms starting last Friday were supposed to move to our new buildings.
Oh, interesting. Okay.
Yeah.
Where are they having everyone? Where are they putting everyone? Or are they just spacing everyone out?
It depends on where you're living. So I believe so if you're for some people they're still gonna be in the same building but a different room.
Okay.
As for me, I have to move to a completely new building. So
Wow.
I, yeah, my place is pretty messy.
Sure. So are you in your new place right now, or did you?
Oh, I'm still in my
Okay.
assignment, and then after this class, I'm going to be moving
Sure.
stuff out.
Yeah.
Yeah,
I totally understand. People have to move. That's kind of a big deal. Um,
yeah.
just want to make sure. Let's see. It looks like I think just about everyone's here. Maybe one person isn't, which is fine. So
Okay.
welcome to class. Let's see. I feel like there were a couple things I wanted to say. Oh, again, here is the link to the attendance form. I didn't spell attendance right, but that's okay. If you all could go fill it out real quick, that would be great. It'll make my life easier. And I'm going to have you do that each class just because it's a really convenient way to keep track of everyone's attendance. And then it's also easy for me to enter it into the system later, which is something that will have to be done eventually. Um, what else? So let's see. I feel like some people had some questions about how to upload the quiz. So I just want to share my screen with you guys real quick just to make sure everyone's on board with it. Um, here's what should work. So if you go to the class, if you go to assignments, and then you click on the quiz, you can click up here on the link to actually get the quiz. Right, and there it is in all its glory. It's 4 questions. It shouldn't be too bad. Um, and then after you finish the quiz, writing it on whatever, if you want to print that out, that's great. If you don't, that's also fine. Once you've done that, then you can click on the bottom link here to load the quiz in the new window, and that'll actually take you to Gradescope. And then your Gradescope might look a little bit different than mine, but I imagine you will somehow click on quiz 1, and then you will be hopefully prompted to upload something. Does that sound? I know a couple of you have done that, so yeah, okay. Mine obviously doesn't do that because I am the teacher of the class, but you should be able to submit something. I think it might also ask you to identify like what questions are answers to what questions. So if you could do that, that would help. I know some of you already submitted it before I edited the outline, that's fine. But if you haven't submitted it yet, when you do submit it, if you could try to kind of make your where you've answered questions correspond to the questions they're answering, that would help me out a bit. I think that's all I wanted to say about that. Actually, there was one other thing I wanted to say about Gradescope though. So just wanted to point out, if you look at Gradescope, if you look at the calendar on Gradescope, you can see, well, actually mine's blank because I unchecked everything, but you can click on, so like for those of you in Rodriguez's class, you can click on that and it shows you all the things that are happening in the class. So these are all, I think, when the class meets. Or if you look at Rodemacher's class, so now that he also has all of his meetings, which is not super helpful. I was trying to show you guys something that was actually useful. One sec, let's see who else. I know somebody, anybody? I was trying to show you guys someone who had like a quiz. Well, so like in this other person's class for 17A, you can see here they have like a different sort of thing due. This is a homework assignment that's due, which I can't seem to click on now. Anyway, what I wanted to show you, which I'm not finding, unfortunately, is someone who has like a quiz that's due in Canvas, and it shows you like a little rocket symbol next to it. So that'll show you something that's due in Canvas, which might be helpful. But here's the calendar. If you haven't looked at it, you might want to look at it. It can kind of help you figure out what's happening in each of your classes and when things are due and when they're not. If you look at our class, Co-17C, you can see here's where the weekly participation points are due. Here's quiz one. Oh, interesting. Somehow quiz one, I think I might have messed up the time for quiz one. Oh well, that's fine. But it shows you when the quizzes are happening. It also shows you when the reflections are due by. It doesn't show the poll on here, and I'm not sure exactly why, but I'll try and figure it out later. It's not a huge deal. Okay, that's enough of me sharing my screen. So let's make sure I pin myself here so that my video is large later on. Great. So I have a couple ideas of things to cover, but is there anything you guys have that you definitely want to talk about today?
Could we go over the higher order partial derivatives potentially?
Sure.
So,
Are
you
you guys talking about mixed partials as well?
I think so.
Okay. Where you like x then y or y then x?
Yes, yeah.
Okay. Yeah, for sure. We'll definitely do that. Before we do that, though, I think I want to talk just a little bit. I want to do a couple more limit examples, just because people still had a few questions about that, and maybe briefly touch on continuity. Oh, come on, chair. This chair is just, this room could just be a tiny bit bigger and it would be excellent. It's not quite big enough. So someone asked in some spot how to know kind of what path to pick. And the answer is there isn't a really good answer. The answer is it's kind of trial and error. You just keep trying things until you kind of run out. Most of the time it ends up being a power of x pretty easily. But let's look at a couple examples here. So I've got the limit here as xy goes to 0, 0. What was it? X to the fourth minus 4y squared over x squared plus 2y squared. And there's a lot of things you could do.
James?
Oh yeah.
What's in front of the y squared on the
That's
numerator?
a 4. Sorry,
it's a 4.
Yeah, I stuck it in there after the.
Okay, thank you.
So, what should we try? Well, I always, maybe not in a good way, I like to start with y equal to x, which is kind of, well, no, really, I would start with y equal to 0 here. So I start with y equal to 0. I get the limit as x goes to 0 of, so all these things go away. I get x to the fourth over x squared, which is the limit as x goes to 0 of just x squared, which is 0. And then I might try y equal to x. If I do that, if the limit as x goes to 0 of x to the fourth minus 4x squared over x squared plus 2x squared. So it looks like, this looks weird. So if I factor out an x squared on the top and the bottom, I get the limit as x goes to 0. I might be wrong, it might not look weird. X squared times, on top I've got x squared minus 4. On the bottom I've got x squared times 1 plus 2. I suppose I could have combined that as 3x squared. I didn't though. And then these cancel. The rest of the x's go to 0, and I get 0 minus 4 over 3. I'll write that again. So since these are different, the limit does not exist. And that's going to happen a lot. A lot. Like a lot of these limits are just going to not exist. What I really kind of want to emphasize is you guys should always be checking out the y equals 0 and the x equals 0 path if you're going through 0, 0. It's one that I used to forget all the time as a student, but it really often gets you something that's useful. So let's look at one more example here. Sure. How about this one? How about the limit as xy goes to 0, 0 of, what have I got? 5y to the 4th cosine squared of x over x to the 4th plus y to the 4th. And so again, so here actually, so 0 doesn't always get you 0, meaning if you set x or y equal to 0, it often gets you 0, but it didn't in the last one, right? In the previous one, oh, it did actually. In the previous one, if I had set x equal to 0, I would have gotten the limit as y goes to 0 of negative 4y squared over 2y squared, and those would have canceled, and you would have gotten negative 2. So 0 doesn't always get you 0. It often does, but not always. That's also the case here. X equal to 0 is not going to get us 0. Here's why. Well, if x is 0, the limit is y goes to 0 of, let's see, 5y to the 4th. And what's cosine of 0?
One.
Yeah. So you get 5y to the 4th over y to the 4th. The y to the 4ths cancel, and I just get 5. Why don't you guys do the other 0? See what happens when you set y equal to 0. So hopefully you're getting 0, because if y is 0, I've got 0 on top, and I've got x to the 4th plus 0 on the bottom. And that limit is 0, because 0 divided by not 0 is 0. This is the limit as x goes to 0 of 0, which is 0. So again, this limit does not exist because two different paths gave you two different values. Just as a quick aside, unrelated, I wanted to mention that you're all very welcome to send me an email, and I'm happy to respond to them. But I also wanted to point out that if you wanted to, sometimes instead of sending me an email, you might be better served by starting a discussion thread in Canvas, because if it's something that someone else might have an answer to, like a couple of you have asked me questions about quizzes, and while I was definitely able to help, I'm sure a couple of you already could have answered that question as well, because you know you did the thing already. So if you want to ask a question that you think other people might be able to answer as well, go ahead and do it in Canvas, because that's going to be easier for me to manage in the long run, to be perfectly honest. It's not been a problem for me so much, but a couple of my coworkers are getting lots and lots and lots of emails. So I just want to preemptively kind of say, like, if it's something you think can be a discussion, start a discussion in Canvas. It'll be easy for everyone. And also, it might be asking and answering the question for someone else as well. So, yeah. I think in my 16B class, they've definitely been using the discussion a lot and kind of helping each other figure out what's going on with their instructors' homework assignments. So feel free to use that. Also, I didn't see, does anyone know, did Rodriguez post more content later? Because I know he ended class early.
I didn't have time to check back
Okay,
yet. I was,
I'll look later and see.
yeah.
I'm sure he'll post something eventually. All right, let's look at a couple of continuity examples, and then we'll get to Cameron's questions about partial derivatives. Everyone's questions for it. So continuity. So really the question we're still going to be asking here is if a limit exists. Because when we're talking about continuity, the same sort of idea about continuity is true in that for a function to be continuous at a point, the limit exists, the limit has to exist, the function has to exist, and those values have to be equal. So just as a real kind of straightforward example, I don't know, let's say I've got sine of xy over x squared plus y squared plus 1. This function is continuous everywhere. It exists everywhere, right? There's no value of x and y that make this function not exist. And these sorts of rational functions, if you don't have any kind of 0 over 0 parts or 0 in the denominator parts, most of the time there aren't any problems. So I would say that this function is continuous for all xy in R2. Every pair of points, you've got continuity there. If you look at the surface of this graph, we could maybe. If you look at the surface, so graphically, the way you can tell if something is continuous or not is if you have like weird kind of jumps or edges in your three-dimensional surface. Which again, not that we're good at graphing those, I'm certainly not. But if you use that tool in Desmos, you might be able to see how this is nice and continuous. Whereas this next example, where'd you go here? Sorry, one sec. That one. This function, g of xy equal to x squared minus y squared over x squared plus y squared when xy is not 0, 0, and 1 when xy is 0, 0. So is this function continuous? Specifically, is it continuous at 0, 0? It's definitely continuous everywhere else. Right? Everywhere else, the function's defined. If x and y aren't both 0, the denominator isn't 0, you're well defined, and the limit's going to be fine, right? Like, for example, is this function continuous at, what was the point I was saying? At 3, 4? Sure, because f of 3, 4 is 9 minus 16 over 9 plus 16. And the limit as xy approaches 3, 4 of this mess, well, you just find the limit by plugging in 3 and 4 because it's not some weird 0 over 0 thing. So 3, 4, oh yeah, the limit exists, the function exists, and the values are the same. So it's continuous there. On the other hand, is it continuous at 0, 0? Well, we know what, oh, sorry, I started using F, but I should have said G. Apologies. I know that G of 0, 0 is equal to 1 because that's the way I defined it. So the question really is, what about the limit as x goes to 0, sorry, as xy goes to 0, 0 of, sorry, I wrote that kind of wrong. And I'm pretty sure this limit doesn't exist because if I let x equal to 0, I'm going to have the limit as y goes to 0 of negative y squared over y squared, which is going to be negative 1. But if y equal to 0, then I have the limit as x goes to 0 of x squared over x squared, which is 1. So the limit does not exist. Meaning this function is not continuous at 0, 0. Because even though the function exists there, the limit does not exist there. Okay, I got one more example for you guys. Oh, sorry. Similar kind of example. F of xy equals the function 8x squared y over x squared plus y squared when xy is not 0, 0 is equal to 0. And xy is equal to 0, 0. And of course, the question we are interested in asking is this function continuous at 0, 0? I hope that it's moderately clear that this function is continuous everywhere else. At any other pair of points that aren't 0, 0, this is going to just easily exist, and the limit is just going to be found by plugging in those values, right? Just like the previous one. 3, 4. So this is here. This function is definitely continuous at 3, 4. Because f of 3, 4 is something, and the limit as xy approaches 3, 4 is that same something. But what about 0, 0? Well, we definitely know that f of 0, 0 equals 0, right? We decided that when we wrote the function this way. So the question we really want to know is, how about the limit as xy goes to 0, 0 of 8x squared y over x squared plus y squared? Now this is actually going to exist. I'm not going to go through the process of showing you a bunch of different paths that all end up being 0. They all end up being, so if you let x equal 0, y equal 0, x equal y, you get lots of things, they all end up being 0. So how do we show that something exists? Well, it's one of those squeeze theorem things. So we know this. We know that x squared is less than or equal to x squared plus y squared. And it's also true that it's bigger than or equal to 0. So if you're doing the squeeze theorem sort of thing, the thing you're trying to take the limit of has to end up being between two things you are able to take the limit of. So then I'm going to try and make this middle part look like this. So first I'm going to divide by x squared plus y squared. 0 divided by something is still 0. And x squared plus y squared divided by x squared plus y squared is just 1. So that's what I've got so far. And now I still need to multiply by the 8 and the y. So I should say, to get to here, I divided by x squared plus y squared. To get to the next step, I'm going to multiply by 8y. 0 times 8y is still 0. X squared times 8, so right, a fraction times something that's multiplied at the top. So I'm going to have 8x squared y over x squared plus y squared is less than or equal to 1 times 8y is 8y. And that's good. That's good because then I can say, oh, look, the limit as xy goes to 0, 0 of 0 is 0. And the limit as xy goes to 0, 0 of 8y, well, y is going to 0, so plugging 0, you get 0. So since the limit of this part is 0, and the limit of that part is 0, the limit of the middle part has to be 0 by the squeeze theorem. So usually you're supposed to say something like, so by the squeeze theorem, the limit as xy goes to 0, 0 of 8x squared y over x squared plus y squared is equal to 0. Which shows us that our function here, I'm just going to say this function instead of writing it out, is continuous at 0, 0. But I'll say most of the time for us, continuity is going to come down to, well, one, does the function exist there? And then if the function exists there, because we've kind of defined it to exist there, does the limit of the other part kind of equal what it's supposed to equal?
Question?
Yeah.
When you mentioned about when you were putting the 0, x squared is between 0 and x squared plus y, you said that your middle term has to be between two things that you can do what to it?
That you can take the limit of. And specifically,
okay.
So I'm trying to make this middle thing look like the thing I'm trying to take the limit of. And I started with this because I knew I was supposed to be really honest. Because I'm kind of, we're often using the fact that x squared over x squared plus y squared, or y squared over x squared plus y squared is less than or equal to 1. So I started with this, and then I tried to make the middle part look like the thing I actually want to take the limit of by dividing by that and then multiplying by 8y. And so the other important thing is though that you're able to take the limit of the other outside pieces and their limit is the same, right? The limit of this is 0 and the limit of this is 0. And since they're the same, then the limit of the middle part is also equal to 0. If you get different values for those, you get nothing. Yeah, good question. All right, let's talk about some partial derivatives. Okay, and there's a couple ways of writing these, which I will try and show you both of. So let's say we have a function, f of x comma y is equal to x cubed times y squared plus cosine of x minus sine of y squared. Seems like a reasonable example. And I want to find the partial derivatives, meaning I want to find fx, the partial with respect to x, which you can write like this, or you can write as del f del x. It's not a d, it's a del. It's like a curly d. So either way, what you're doing when you find the partial with respect to x is you're saying, I'm going to treat y like it's a constant. And really the idea is, let's pretend like we're on some surface, right? My surface is not great. Oh well. And if you're taking the partial with respect to x, you're saying, if I move in the x direction, how does the function change? So you're asking, how is f changing as x changes? Well, if x is changing, if you're moving in the positive x direction, y isn't changing, right? The y values are staying constant. And so we treat them as constants when we differentiate. Let me erase this over here. So when I look at x cubed times y squared for del f del x or fx, I'm really thinking of y squared as like 7. I'm thinking of this as x cubed times 7. And the derivative of that is 3x squared times 7, or my y squared. And y squared is just, in this case, y squared is a constant multiple. And when you have the derivative of, 7x cubed, the derivative is 7 times 3x squared, which is 21x squared. Those constant multiples just hang out. Okay. The derivative of cosine of x is minus sine of x. And the derivative of sine of y squared is
Sine of y squared.
Yeah. The derivative sine of y squared is 0 because we're treating y as a constant. This whole thing here, since there's no x's in it, and we're differentiating with respect to x, the derivative of this part's just 0. So here's our partial with respect to x. It's 3x squared y squared minus sine of x. Let's go the other way. Let's find fy, which is del f del y. So now, from this, I'm going to treat x like a constant and y like the variable. So constant times y squared, the derivative is the constant times the derivative of y squared, which is 2y. Okay, everybody, I want you to think about and tell me if you're feeling like it. What should the derivative of cosine of x be if I'm differentiating with respect to y?
0.
Yeah, definitely. And then the derivative sine of y squared is going to actually have some stuff. So the derivative sine of some stuff is cosine of the stuff, but then I have to multiply by 2y because of the chain rule. Okay. So you can also take, well, so there's really lots of partial derivatives you can take. You can do repeated partial derivatives. So we could also find, say, fxx, which is the second derivative with respect to x, or the second partial with respect to x. So all I'm doing, just like I did with regular derivatives, is I'm looking at the first derivative with respect to x, and then differentiating that. So I'm going to get 6x times y squared. Again, right, this is a function, this is a constant, and the derivative sine of x is cosine of x. That doesn't look very nice. Fyy is going to be a little bit more work. That's del squared f del y squared. And that's equal to, so differentiating this with respect to y, I'm going to get x cubed times 2 minus, here I'm going to have to use the product rule. So I'm going to do the derivative of cosine of y squared, which is negative sine of y squared times 2y times 2y, right? There's the derivative of that times the other piece, plus, then we leave this part alone, so it's cosine of y squared times the derivative of that, which is 2. And that would be your second partial with respect to y.
Shouldn't the part where it says cosine y squared times 2, shouldn't that be minus because of the minus from the
Actually,
partial
no.
y part?
Here's the thing. I kind of thought of it as minus that product. And so I've got minus the derivative of that product.
Oh, okay.
If we distribute the minus sign, then it'll totally be what you think, right? You'll get the plus here and the minus there.
For the f of x of y, or f of double x, could there be f of x of y?
So yes, but so before we do that, I want to help you say it the way we're supposed to say it. So when you say f of x, you mean the function of x. So the way we actually say these partials, you just say fx or fy or fxx or fyy. You can also say this, but that's a lot more, right? Saying del f del x or del squared f del x squared is a lot of saying. But yes, we can definitely, we're going to do the mixed partials right now. So let me go to the other side. So, and there's something cool about the mixed partials. Well, cool might be an overstatement, but there's something interesting about the mixed partials. Yeah, I don't remember what the property is actually called now, but we're going to see. So let me actually get these back real quick. So del f del x, fx was 3x y squared. Fy was x cubed 2y. Okay. So, also an interesting thing about notation. So fxy, the derivative, the mixed partial where you take the derivative with respect to x first and then y second. If you write it using the Leibniz notation, the del notation, it looks like this. It's del squared f del y del x. The order gets reversed. Well, it's not so much reversed, it's just that this means you do x first and you do y first. This means you do x first and then you do y second. Sorry, I said y first over here. This is x first, then y. This is x first, then y. And this notation, if you actually want to write it out, it's actually this. Right? It's the derivative with respect to x, and then it's the derivative of that derivative with respect to y. This notation is a lot faster to write, obviously, but you should know that when you write, depending on the notation you use, they're backwards from each other, which is kind of unfortunate. Except that it's not that unfortunate because, well, let's actually do it and then we'll see why. So if I find fxy, I'm taking the derivative of fx with respect to y. So I might write this for just a second. It's the derivative with respect to y of all this. 3x squared y squared minus sine of x. So now if I'm differentiating with respect to y, 3x squared is a constant times y squared is a function. I'm going to get the constant multiple times the derivative of y squared is 2y. And everybody should be able to tell me that the derivative of sine x is what? Let's hear some voices. Or not. So the derivative with respect to x of sine x would be cosine x. But if I'm differentiating with respect to y, the derivative of sine of x is a big old 0. So again, whenever you have something that has none of the variable, it's a constant. And its derivative is always going to end up being 0. So we get, I'm going to simplify this as 6x squared y. Let's do it the other way. Let's find, in fact, why don't you guys find fyx? So you're going to take the derivative with respect to x of fy, which was x cubed times 2y minus cosine of y squared times 2y. Go ahead and find that. It shouldn't be too terrible. So derivative of x cubed is 3x squared, and the 2y multiple hangs out. And the derivative of cosine of y squared times 2y is 0. I should really say the derivative with respect to x of cosine of y squared times 2y is 0. So look what I got. I got the same thing. So here's what's mostly true. This is generally true, and I think for our class, it's pretty much always true. There are some examples where this is not true, but it is usually true that the mixed partial fxy is equal to the mixed partial fyx. That's not always true. There's a, and I don't remember the name right now, but there's a name for functions that meet this criteria. But I will tell you, to come up with an example that where this is not true, it doesn't look normal like this. Like you usually have to come up with some weird kind of piecewise function to find an example of a function where the partials do not equal each other. The mixed partials do not equal each other. And I can do that for you guys later, but I don't think it's really the focus of this class, so I don't imagine it's really that necessary for us to cover that. Okay. So what about this new function? G of xy equal to e to the 8x squared y. Let's find some partial derivatives. So I want to find gx. So I remind you, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the 8x squared y is e to the 8x squared y times the derivative of this with respect to x is going to be 16xy. Right, the derivative of 8x squared is 16x, and the y is just a constant multiple that hangs out. Right. I want you guys to find the partial with respect to y. Go ahead and give that a try. I was trying to find the thing. So we end up getting here, let's see, I get e to the stuff, and then the derivative of ax squared y with respect to y is just 8x squared. And then we can find the mixed partials. So here's the thing, eventually, I don't remember what section it's in, but eventually we're going to use all the second derivatives, so gxx, gyy, and gxy, or gyx, to determine whether a function of two variables has a maximum or a minimum or a saddle point at a critical value. So that's eventually where we're going to go with some of this stuff. There's other stuff too, but that's kind of one of the main things. So if I was going to find gxx, so I have to take the partial of x with respect to x. So I'm looking at this function here, and I see that I have to use the product rule, right? I've got one function of x times another function of x. So derivative of this is going to go, I might want more room. I'll write down here. I thought I wanted to go up there. I didn't know. So gxx is going to equal, let's see. So the derivative of this is actually this whole thing. Right? It's e to the 8x squared y times 16xy times 16xy. Right? If you want for a second, some people like to call this like u and v to remind themselves of the whole product rule thing. So this part here, there's my u prime times my v plus, then I do it the other way, right? I leave the first thing alone. You get e to the 8x squared y, and then multiply by the derivative of this with respect to x, which is just 16y. Because again, this is my only variable when I'm doing it with respect to x. Derivative of x is 1, the rest of the constant multiples just stick around. All right, why don't you guys find gyy? So again, you're going to take, the derivative. Now, gyy is going to be a little bit easier. You're going to do the derivative of this with respect to y. Tiny bit easier. So here's what I'm seeing for GYY. So here, this function, there's my only y. So I'm just thinking this is a constant, whereas this wasn't a constant for gxx, but this is a constant times this function of y. So the derivative is going to be, that constant's just going to stick around, times the derivative of this with respect to y, which is e to the 8x squared y, times the derivative of the stuff is just 8x squared. If you wanted to, let me actually make this look nicer here. If you wanted to, you could have used the product rule. You could have said, okay, it's the derivative of this. So in fact, it's right here. So it's the derivative of this, which is right here, u prime, times that, which is v, plus this, which is u, times the derivative of this with respect to y, which is 0. Which is why I didn't even write it, because, well, I didn't even need to use the product rule, right? I could have just said, oh, this is just a constant times the function, and the derivative is the constant times the derivative of that function. That's what's happening there. How much time we got? Not that much. I feel like we should do the mixed partial as well. So here's the thing I would encourage you to get in the habit of doing. Don't do the mixed partial both ways unless you absolutely are required to. If you do it one way, I mean, maybe they're going to ask you to like show that it's the same either way for a function you're doing, but in general, it should be the same. So once you found gxy, you have also found gyx. But we can definitely do gxy. So here's the thing, it also shouldn't really be harder one way or the other. So if I look at this, differentiating with respect to y is going to require the product rule. If I look at this, differentiating with respect to x is also going to require the product rule. Right? It should be similarly difficult either way. So let's do this one. So let's find gyx, and that's going to equal the product rule. So I'm taking the derivative of this derivative with respect to y with respect to x. So derivative of that. So I'm going to get u prime. Sorry, it's e to the 8x squared y times the derivative of this with respect to x, which is 16xy, times this left alone. So here is my u prime v plus, leave this alone, e to the 8x squared y, that's my u, times v prime, which is just 16x. So that is how that one's going to look there. You could definitely simplify this, right? Like if you needed to kind of, if you're trying to set this equal to 0 for some reason, you could totally factor out an e to the 8x squared y. You could also factor out a 16x. It's probably not super necessary, but it is something you be aware of. But yeah, that's a good beginning on partials. What I want to really stress about partial derivatives is if you're differentiating with respect to x, you have to pretend that y is a constant, and vice versa. If you're differentiating with respect to y, you have to pretend that x is a constant. So if you see if you're differentiating with respect to x, and you see a thing with just y's in it and no x's, its derivative is 0. If you're differentiating with respect to x, and you see something with x's and y's, then you treat the y things as a constant multiple. You just kind of leave them there and differentiate just the x parts. So just as one more quick example, if my function was something like, let's not make it too awful, James, e to the x cubed plus y cubed times cosine of y squared times, divided by, what other trash can I throw in there? Y squared plus 1. So I want to find fx, which is good because fy would be terrible. So first of all, I'm going to rewrite this just slightly. And I recommend this if you've got exponents where different variables are added together, I think it's really worth your while to think of this as e to the x cubed times e to the y cubed times cosine of y squared divided by y squared plus 1. And then I really kind of want to think of, hey, it's really just e to the x cubed times all that other garbage, right? This is e to the x cubed times all of this stuff with y's. And the derivative with respect to x, well, this is a constant multiple. It's just going to hang out. The derivative of e to the x cubed is e to the x cubed times 3x squared times all of this constant that just sticks around. So it's actually not terrible, even though it looks kind of terrible. All right, it is 2 o'clock. Two things. If you have other questions you want to see me talk about, I'm happy to make more videos. I would say you can send me an email, but it'd probably be better if you started a discussion thread on Canvas if you want to see me make something. I'm really happy to do it. I've got a fair amount of time to make videos, so I can do this. I know some of you have been watching them. The other thing I want to say, which is totally unrelated to class, is I watched a really great video of the original cast of Hamilton singing the opening song to a girl who's 9 who didn't get to go see Hamilton. There's a link to that video. It's the Hamilton part starts at like minute 8.5. The previous part's like John Krasinski talking about other things. But if you like Hamilton, have heard of Hamilton, you should watch that. It's pretty entertaining. And I listened to it and I was like, did they just like play the recording over it? Because they sound really good. So watch that. I'll leave it up there for a minute if you want to grab it. And yeah, good class. I'll see you all on Wednesday. Don't hesitate to get in touch if you have questions or want to see things. Bye.
Thank you.
You're very welcome.
Thank you.